Hello everyone, let's continue this session. In the last session, we solved the problem number 1 from workbook and we calculated what is voltage gain, and along with voltage gain, we calculated current gain, input impedance, and finally we calculated output impedance also. Then we had some observations. The observations are common emitter amplifier is having very good voltage gain and very good current gain, but because of not having impedance matching, we are not able to utilize as they are, right? I hope that is what is clear. Now when I say impedance matching, right, it is not like Ri is equal to Rs. I told you this point already. The impedance matching is nothing but what is the input impedance to match Vi to Vs. What is input impedance to match Vi to Vs? That is what is called input impedance matching. Similarly, output impedance matching, to match V0 to AV into Vi, what should be R0? Therefore, to match V0 to AV into Vi, what should be R0? That is what is called output impedance matching. It is not impedance matching, it is what is output impedance to match voltages. Therefore, impedance to match voltages, impedance matching for voltages. That is what I told, right? We need Ri to be very high. If Ri is very high, Va will be matched to Vs. And if R0 is very low, almost zero, then V0 will be matched to AV into Vi. Therefore, we need Ri very much greater than Rs and R0 very much lesser than RL to get impedance matching for voltage amplification, because I am speaking about voltage matching even though we are not speaking impedance matching. That's why I am saying impedance matching for voltage amplification. I hope this is clear. Similarly, if I say current amplification, then I want Ri for current amplification or current matching. Similarly, I want R0 current matching. That part I will explain later on, but remember, this is only specific to voltage amplification. This is only specific to voltage amplification. Only for voltage amplification, ideally I want Ri infinity, R0 0. This is what is the summary we got yesterday. And a common emitter amplifier, it is not having proper impedance matching, but it has very good voltage gain, very good current gain. Because of not having impedance matching, ultimately we are getting voltage gain minus 200. We have to live with the gain which is minus 200. If you have impedance matching from both input side as well as output side, let us say, then we would have got the voltage gain very high, right? Because of not having impedance matching, we are getting minus 200. Okay, this is what is the summary. Now let's go for second problem. I think from workbook. Now the second problem number 2. Let me erase everything. Problem number 2. Problem number 2. Calculate all AC parameters related to the following circuit. Okay, that is what is the problem. And the AC circuit is given along with power supply, no biasing circuit given. That is what is specified in the problem statement, right? Therefore, only asking for AC parameters. Anyway, we are looking for AC circuit, right? Then the circuit is this is what is given as Rn, which is 10 kilo ohm, and this is defined as V0, and this is power supply VCC, and This is what is our practical voltage source, Vs, and Rs is equal to 1 kilo ohm, and this is input voltage to your amplifier. Real input voltage is Vs, right? But it is practical voltage source because of Rs. Okay. Now, but the actual input to your amplifier is Vi, and this is nothing but your load resistor, which is 10 kilo ohm, and then we are applying from transistor, we are applying voltage V0 to your load. Okay. Vi is the one which we are applying to your amplifier, V0 is the one which we are applying to the load. Done. This is what the circuit. Now asking for all AC parameters. When I say all AC parameters, default 4 AC parameters which we studied: voltage gain, current gain, input impedance, and output impedance. Okay. Now calculate all. Right? Instead of asking for one parameter, I am asking you to solve all, because we know what and all important to get like different AC parameters. Right? Let's see. Now, according to our procedure, the procedure whatever I have given in the last session, right? The first step is, first of all, decide AC analysis or DC analysis. Obviously, the problem is AC analysis because asking directly AC parameters. Then next step, we need to find AC circuit. What is AC circuit? Remember, every time we need not draw what is AC circuit from the given circuit. If you solve multiple problems, you will be automatically analyzed what will be the AC circuit, then from which we can calculate the configuration, because the next step is to find the configuration from the AC circuit. Therefore, in the examination, it is not subject to examination, this is objective. Therefore, it's not that we need to, first of all, what is AC circuit, what is the configuration. That is for our understanding purpose. To make it faster, you need to visualize it and get AC circuit without touching the original circuit, then continue. If it is giving some confusion, yes, let it take some time, no problem. We want accuracy, not the speed. Speed is also important, but accuracy is very important. Therefore, you can draw AC circuit and then you can find the configuration. That is your wish. Okay, because you are in the initial phase, maybe for your understanding, let me draw AC circuit also. Then for what? AC circuit to find the configuration, right? Without drawing AC circuit, if you are able to find configuration, that is well and good. Okay. Now, where are we applying the input? Now we are trying to find the configuration. Where are we applying the input? We are applying the input at base with respect to ground, right? Where are we taking output? We are taking output at emitter with respect to ground, right? Applying input at base with respect to ground, taking output at emitter with respect to ground, right? Now, I told you for AC analysis, right? For AC analysis, we should keep AC source, then dynamic resistance, RS, dynamic circuit, which is H parameter model, which we already replaced, and assume that we replaced, and then dynamic resistance of your load, RL is RL, because dynamic resistance or static resistance both are same. Therefore, dynamic resistance, then dynamic resistance of power supply. What is dynamic resistance of power supply? Or internal resistance of power supply, or AC resistance of power supply, or equivalent resistance of power supply, or incremental resistance of power supply, which we had seen before. Therefore, that is 0. Therefore, dynamic resistance is 0, means we need to replace with dynamic resistance or AC equivalent resistance. Therefore, we know that this is what is the battery, which is what is connected to ground. If this is the battery which is connected to ground, for AC analysis we need to short, because we are replacing with dynamic circuit. Therefore, replacing with short circuit, then can I say your collector is now connected to ground. Physically we are not shorting it to ground. I am repeating this statement again, which I already told in the last session. Physically we are not shorting this VCC to ground. Then why are we shorting it to ground? That is for our analysis purpose. That is what is called AC analysis, because during AC analysis we don't bother, or it's not we are bothering, we don't need to consider the DC quantities. Not only power supply, maybe if there is any DC quantity, that can be ignored during AC analysis. Okay, but during DC analysis, the signals which are changing with respect to time, those can be ignored. The signals which are changing with respect to time, example, the actual input signal itself, those things can be ignored, only respond to DC quantities. That part we will see after completing AC analysis, right? Therefore, now Do you want me to draw AC circuit also? Maybe let me draw for the circuit, or later on as we continue I will not draw specifically AC circuit, right? If I draw AC circuit, what is that? The transistor to be replaced with H parameter model, because that is dynamic circuit of transistor. Now, and this is what is the load. This is your, or maybe let me draw to match the circuit to the block diagram what we had seen. Right? Now, this is what is our transistor. Can I just extend the load something like this? Yes, because it is a wire, right? We can extend it. What is RL? RL is equal to 10 kilo ohm, and this is what is your V0, right? And now, because I am speaking about AC circuit, this VCC is connected to ground. Therefore, this VCC is connected to ground. I am just grounding here. I am saying that this is nothing but your AC ground. This is AC ground. Okay, and your input, we are applying input with practical voltage source. Therefore, this is your Vs and this is Rs. Rs is equal to 1 kilo ohm. Now the input is nothing but this is what is our input, which is what is applied. Okay. Now if I represent like a block diagram, therefore this is what is our block diagram, right? Now we know that this is collector, this is base, this is emitter, right? You think, therefore we are applying the, if you think like a black box, right, something is there inside, then input is there, output is there, right? Therefore this is what, now using this, because this is basically BJT only, and then we replaced BJT with H parameter model and we solved the equations and we got AC parameters derivations. Now, but we need to find the configuration. Only when you know the configuration, then only instead of HI, which is generic, we can say HIE, HIC, HIIB. Okay? That is what. That's why our second step is to find the configuration. Only when you know the configuration, then only you can take proper H parameters related to configuration. Okay? Now, what is this configuration? Applying input voltage at base with respect to ground, collector is at ground, taking output voltage at emitter with respect to ground, collector is also at ground, basically AC ground, what may be ground. For both input and then output, your collector is common because ground is common, right? Therefore, this is what is called, but don't think that because collector terminal is not physically connected to what we call the ground here, therefore no. Remember when I say this is ground, this is ground, this is ground, all are shorted but not showing physically with a wire, okay? That is fine. Therefore, if I repeat, this is nothing but common collector amplifier, because applying input voltage at base with respect to ground, taking output voltage at emitter with respect to ground, collector is at ground, therefore common collector amplifier. This is CC amplifier. Right? Now, once you know the configuration, then immediately apply the formula what we derived, which is blind. Okay? I think you can try. What is the first one? The first one is nothing but current gain. That is what is the flow which we need to follow. Current gain, input impedance, voltage gain, output impedance. Okay? What is current gain? Minus HFC. Now I am replacing with C because common collector amplifier. Divided by 1 plus HOC into RL. Okay. Now, what is HFC? I always prefer to convert into CH parameters, and remember CH parameter value, then it is easier. Your own way. If you directly substitute what is HFC from the given problem statement, you can go on. But sometimes, as I told you, sometimes the CH parameters will be given, but the problem is related to CC amplifier. Then surely we need to convert the CCH parameters into CEH parameters. Then let me convert into CEH parameters. What is HFC? If you go back, right, I gave the H parameter values for different configurations and I gave the conversion formula as well. Therefore, if you refer that, what is HFC? HFC is nothing but minus 1 plus HFE, minus into minus plus, then it will become 1 plus HFE. divided by 1 plus, what is HOC? HOC is nothing but HOE only into RL. Okay. Now we know H parameter values. 1 plus HFE. What is HFE? Typical value which I gave 50. Therefore 1 plus 50, 51 divided by 1 plus, what is HOE? 1 by 40k. What is RL? 10k. Right? And small assumption which is valid. Can you treat 51 as 50? Maybe for your understanding, can I say, can you neglect 1 rupee out of 51 rupees? Then can you take only 50 rupees? Yes, obviously. Right? If you say that I don't take, means I want only 51 rupees. Similarly, go ahead with 51. You need a calculator. I am saying without calculator it is very easy, but it is accurate. Okay. Now, when I say 50, then what is 10k by 40k? Kk will be cancelled. 10 by 40, 1 by 4. 1 plus 1 by 4, 5 by 4. 5 by 4, it will become 4 by 5. If I treat it as 50, 5, 10, 10 into 4, 40, right? You'll get 40 point something because of 51, but I'm taking it as approximately 40. Therefore, you are getting current gain 40. Let me put in the box because ultimately you are looking for it. For the problem statement, we need to find AC parameters. Once you find AC parameters, problem is over. But we are solving the problem not to solve the problem. We are solving the problem to understand or to have the observations and then look for, are we getting required parameters, required specifications, right? Those things we need to have. When you have observations, that will lead to conclusion. That conclusion is standard, which we can take it lifelong. Okay, that's why observations are very important. Fine, the first parameter is over. Now what is the second parameter? The second parameter is Ri. What is Ri? Ri is equal to HIC plus AI into HRC into RL. Right? Now let me convert into CH parameters. Then what is HIC? HIC is nothing but HIE plus AI into, what is HRC? HRC is equal to 1 into RL. Then what is HIE? Right? HIE I already gave 1.1 kilo ohm plus what is current gain, which we already calculated, 40, approximately 40. What is RL? RL is nothing but 10 kilo ohm. Therefore 40 into 10, 400 plus 1.1. Therefore I can say approximately 400 kilo ohm. Either 401.1 or 402, 403, doesn't matter. Therefore this is 400 kilo ohm Ri. Okay, fine. Now let's see the third one, right? Third one, voltage gain. Therefore what is voltage gain formula? AI into RL divided by Ri. AI into RL divided by Ri. Then what is current gain? 40, right? You can substitute, but I want to, if you substitute also you'll get it. But now what I'm saying, without substitution you'll get a formula, derived formula. Now this is nothing but, can I write it like AI into, just simply taking this here, into RL divided by Ri. What is AI into RL? AI into RL, let me take this is star, just to have conversion formula. Therefore can I say AI into RL without substituting the values? Okay, I'm giving generic formula. AI into RL, can I say Ri minus HIE? You can take this HIE to left hand side, right? Then Ri minus HIE. Therefore AI into RL is nothing but Ri minus HIE divided by Ri. Right? This is from star. Therefore this is from star. Now Ri by Ri, that is 1 minus HIE divided by Ri. This you can take it as a formula. Now you can substitute. Even if you substitute now or if you substitute here, both will give you the answer. Don't bother. Okay, that's fine. What is HIE value? Your HIE value is 1.1K, and what is RI value? Now you can substitute. Therefore, 1 minus HIE is 1.1 kilo ohm, RI is 400 kilo ohm. Right? It will give you some feel. What is that feel? Your RI is very much greater than HIE. Right? 400 kilo ohm is very much greater than 1.1 kilo ohm. Kilo will be cancelled. Approximately, let me take 1.1 as 1, then 1 by 400. I can neglect 1 by 400 with respect to 1. Then I can say this is approximately equal to 1 but less than 1. But I can say close to 1. Maybe if you solve exactly, you'll get 0.98 or 0.99, which you can take it as 1. Okay, fine. Now the last one, output impedance, right? What is R naught? R naught is nothing but 1 by Y naught, which is output admittance, right? And then we know what is Y naught? We know that Y naught is equal to, what is the formula? HOC minus HRC into HFC divided by RS plus HIC. This is the formula for CC configuration. Let us convert those CC configurations into CEH parameters. Therefore, if you convert, then what we get? Therefore, Y naught is equal to HOC. Let me convert into CEH parameters. That is nothing but HOE minus HRC 1, HFC minus of 1 plus HFE, minus into minus, plus 1 plus HFE. If you refer the values what I gave, the conversion values, you'll get it. RS, that is source resistance, RS, plus what is HIC? HIE. You will understand why are we converting CCH parameters into CEH parameters, and we will see that. But give me some time, you'll get it. Now, you may say, why don't we convert CEH parameters to CCH parameters? You may ask, right? But in the examination till now I didn't see, even though the problem is related to CC amplifier, people are providing CEH parameters. If the problem is related to CE amplifier, people are providing CEH parameters only. Why only CE? I'll tell you, okay? Therefore, now let's substitute. What is HOE value? Before substituting and then getting actual value, let me give you another formula, derived formula, okay? Now, what is HOE value? Your HOE value is 1 by 40K, which is 25 microampere per volt, right? This is what is your HOE. Similarly, what is this value? This is nothing but, let's calculate what is this value. This value is nothing but 1 plus HFE, which is 51 divided by RS. What is RS in the problem statement? 1 kilo ohm. And this is 1 kilo ohm plus what is HIE? 1.1 kilo ohm, right? Then if you calculate what is this, can I take this 51 as approximately 50? Approximately 50. And can I take 1.1K as 1K? Then 1K plus 1.1K, 2.1K. Let me take it as approximately 2K. Then what is this value? Then this value is nothing but 25, right, milliampere per volt. This is 25 milliampere per volt. Now tell me, 25 milliampere per volt. Now this is 25 microampere per volt. What is the difference here? 25 is common, but this is micro, this is milli. Therefore, this value is 1000 times lesser than this value. Then can I ignore this value? Yes, we can ignore, right? It is like neglecting 1 rupee out of 1000 rupees. We can neglect it, right? Therefore, if you neglect it, then what is your Y naught? Your Y naught is equal to, if I neglect this, 1 plus HFE divided by RS plus HIE, right? Then what is your R naught? Therefore, R naught is equal to 1 by Y naught, which is RS plus HIE divided by 1 plus HFE. This is what you can keep in the bracket. Remember, this is derived formula. The output impedance of CC amplifier in terms of CH parameters, RS plus HIE divided by 1 plus HFE. Okay. Now, if you take this, right, now, actually if you substitute now, right, or if you substitute here the values and get Y naught, almost same only. This is nothing but 1 by 25 only. This is 1 by 25 because reciprocal of this is nothing but your R naught. Therefore, reciprocal of 25 milliampere per volt, 25 milli. Then the milli will become 1000 to the numerator. 1000 divided by 25, 40. Therefore, what is your R naught? 40 ohm. Your R naught is equal to 40 ohm. This is the value. This is the formula. I can say problem is over. Okay, write down. Then later on I'll give you observations. Maybe the people who completed this on your own or from the board, try to have the observations. Whatever we had in the case of CE amplifier, similarly try to get the observations on your own. Then let's see, right, what it gives. Take them. See, for all AC analysis problems, there is an assumption. That assumption is transistor is in active region. Therefore, all these H parameter values, right, and all these formulae are the dynamic circuit of your BJT, which is nothing but H parameter model. They are all valid only when the transistor is in active region. Basically, we want current source. If you take your H parameter model, we have that HFE into I1. That is nothing but your current source. We get current source action from BJT only when the transistor is in, or when the BJT is in active region. That we had seen already in the starting of the class. Specific to this problem, the values AI 40, RI 400K, AV equal 1, R0 40 ohm. Those are not the answers. But in a generic way, covering the theory as well. And AV we got 1 minus HIE by RI. R0 we got RS plus HIE by 1 plus HFE. Then RI, HIE plus AI into RL. And then AI, again same thing, right? It is not specific, it is generic, or it is similar to your CE, but only the AV which we derived little bit, and then R0 which we derived little bit. Okay. Try to solve the workbook problems, maybe before attending any session. Then, because anyways we are going to solve those things in the classroom, but If you try on your own, you'll get the difficulty. Then when I solve in the classroom, you can correlate, and then you'll remember it for a long time, right? Without trying, and if you see directly in the classroom, then yes, you'll get it, you'll understand. But because you don't have the struggle to get the answer, then remembering will be taking less time. It needs more time, or we have to do it multiple times to remember, right? For everything there is a procedure to remember and all. First we need to try, then only you'll understand the pain or difficult. Then after that, if you see the solution, then you'll understand very clearly, because you tried different ways and you didn't get it. Then after seeing the solution, oh, we have to do like that. That is what is the observation of the conclusion, you'll get it. Okay. I hope this is done. Let me give you 2 more minutes, then we will see the observations part. That's why the people who have completed, right, then they can have observations. Is this over? Okay. Now, let's have the observations. Okay. Before going to observations, now if you see here, current gain. What is current gain? 40. Let's go to magnitude later, but we don't have minus sign. If you take common emitter amplifier, we got minus 40, and I explained the meaning of minus. The meaning of minus, that time it was the direction of the actual current, okay, with respect to the load current, because our convention is the current which is what is entering into the load, that is what is the load current, and the current which is what is entering into your amplifier, that is nothing but your input current taken by your amplifier. That is what is our reference direction. Then with respect to that reference direction, if I say positive means our reference directions are true. If you are getting negative means our reference directions are not true, which was the case in the case of, which was the case from common emitter amplifier. Now let's see the actual direction. The actual direction, if you see, this is nothing but what? Our load. Always we took the current which is what is entering into the load is nothing but your load current IL, right? Then tell me, is this true? Is this real direction? Yes, because this is base current, this is collector current, base current plus collector current, that is not your emitter current, that is what is entering into your load, right? Therefore, base current plus collector current, that is what is entering into your load. Therefore, if I say the base current also, this is what your input current IB, let us say. Therefore, your input current, the current which is entering into your amplifier, satisfied. The current which is what is entering into the load, IL, satisfied. Basically, that is nothing but your emitter current, right? Because IB and this is your IC and this is what is your IE. Then your IE is nothing but your IL. Therefore, IE is nothing but your IL, satisfying the direction, right? That is the reason why your current gain is positive. Positive means, therefore let me tell you, whatever current you are pumping into your amplifier, 40 times of that current you are pumping into the load. That is what is your current gain, right? Therefore, whatever current which you are pumping into your amplifier, U in the sense the voltage source, or current source. What it may be. The current which is entering into your amplifier, the amplifier is amplifying the current 40 times and then giving it to load. That is what your current gain, and the directions are satisfied. Therefore, it is pumping into the load only. Done. Coming back to, therefore, that's it. Therefore, now don't bother about current gain, voltage gain, magnitudes. Let us see input impedance and output impedance. Right? Tell me, what is Ri? Your Ri is 400 kilo ohm. Therefore, Ri is 400 kilo ohm. When I say Ri is 400 kilo ohm, is it very much greater than your Rs? That is what we need, right, for voltage amplification. Therefore, now your Ri is very much greater than Rs. It has very good input impedance matching. Therefore, I told you already, input impedance matching. To match Vi to Vs, what is the input impedance? Your input impedance is 400 kilo ohm. If input impedance Ri is equal to the impedance seen into input port is 400 kilo ohm, then it is 400 kilo ohm, this is 1 kilo ohm. You can neglect 1 kilo ohm with respect to 400 kilo ohm, then I can say your Vi will be equal to Vs. Therefore, input impedance matching is satisfied to have Vi is equal to Vs. Fantastic. Now, coming back to output side. If you see output side, what is your output impedance? The impedance seen from the output port when Vs is equal to 0. That is the definition, right? Therefore, what is the impedance seen from output port? This is what is the impedance we are seeing from output port, right? This is easy to understand R0, but if you ask me to represent what is R0 here, how will I represent? We need to exclude and then impedance seen into emitter or impedance seen into emitter with respect to ground. This is easy to represent R0, okay? Therefore, what is R0? We got R0 40 ohm. What does it mean? I told you, if you think like a loudspeaker and this is what is your audio amplifier and this is what your loudspeaker, then your amplifier is the source for your loudspeaker. Can I say in that way? Your amplifier is the source for your loudspeaker. If amplifier is source for your loudspeaker, if I speak about voltage signals, then that amplifier is giving voltage to your loudspeaker, your amplifier is a voltage source. But whether it is ideal voltage source or practical voltage source, that is what is defined by your R0, where R0 is nothing but your internal resistance of the voltage source. You can treat in that way, right, for voltage signals. Therefore, now what is R0? 40 ohm. With respect to 10 kilo ohm, what is 40 ohm? Very small. You can take it approximately 0. What does it mean? There is no internal drop. Whatever voltage which you are getting from your amplifier or from your transistor, that will be exactly applied to your load. Therefore, it has very good output impedance matching. Again, impedance matching means to match V0 is equal to the AB into Vi, whatever you have from the transistor. Therefore, that is what we are trying to apply directly to RL without seeing any drop across R0, because R0 is very small. Therefore, your CC amplifier is providing very good input impedance matching, very good output impedance matching. For what? For voltage amplification, right? What does it mean? Whatever maximum gain, maximum available gain you can get from your amplifier, from CC amplifier, that you can get it without any loss. In the case of CE amplifier, the maximum available gain is 400, let us say minus 400. Then because of not having input impedance matching, that minus 400 became minus 200, right? Here, whatever maximum available gain you have won, without any loss, we can utilize. Tell me, what is that voltage gain which we can utilize? Voltage gain is 1, means we can utilize 1 as it is without any loss, because it has very good impedance matching. See, in the case of common emitter amplifier, we have very good voltage gain, but no impedance matching. Here, we have very good impedance matching, but there is no voltage gain to utilize. Yes, we can utilize this as it is without any loss, but the available voltage gain from your configuration is nothing but 1. Therefore, if you want something, you need to lose something. If you want voltage gain from common emitter amplifier, at least 200, but we don't have impedance matching, that's fine. If you take common collector amplifier, we have very good impedance matching, but there is no voltage gain. But if you compare these two, which is better, I can say CE amplifier is better. Even though it doesn't have impedance matching, which is ultimately giving lesser voltage gain, but at least you are getting minus 200. But in the case of CC amplifier, we have very good impedance matching to utilize your voltage gain, right, which is available. That is nothing but 1. Therefore, your overall voltage gain is 1. Therefore, if you compare which is better for the amplification, voltage amplification, I can say blindly common emitter amplifier. But can we improve? Can we improve the voltage gain from common emitter amplifier? But can we improve the voltage gain from CC amplifier? No, we cannot improve, because improvement is nothing but actually it is not 1.98. You can improve 0.99 or you can improve it to 0.995. Maximum you can get 1 only. More than that we cannot improve. Right? Now, what about C amplifier? We got minus 200. Can we improve? Yes, we can improve. By what? I'll give you the solution. Okay? Now, maybe if you see overall observations between common emitter amplifier and the common collector amplifier, common emitter amplifier is having very good voltage gain and no impedance matching for voltage gain. And CC amplifier, it has very good impedance matching for voltage amplification, but there is no voltage gain. Right? Then what to do? Combine. Combine C amplifier and CC amplifier. If you combine both, C amplifier will give you very good voltage gain, but impedance matching part will be taken care by your CC amplifier by keeping input at the input stage of CE amplifier and at the output stage of CE amplifier. Then overall, this is what is your multi-stage amplifier, but the gain is extracted from this multi-stage configuration from CE amplifier, and the impedance matching part with respect to external world, source to load, that is taken care by your CC amplifier. Right? Let me explain the block diagram, therefore you will understand it very clearly. Okay? Am I clear? Right? Okay, fine. But before giving the block diagram, then what is the purpose of CC amplifier? That is what? The block diagram what I am going to give, that will explain. But before going to the block diagram, the purpose of CC amplifier, or people call the CC amplifier as buffer amplifier. Okay? Let me erase all these things. Maybe before that, let me dictate, then we will see the remaining things from the next session. Okay? Because time is almost done. Okay, write down observations. Whatever I told, I am just dictating. Okay? Write down observations. First observation, CC amplifier is providing very good impedance matching. CC amplifier is providing very good impedance matching. Very good impedance matching. Both input and output. Both at input and output. CC amplifier is providing very good impedance matching both at input and output. Both at input and output for voltage amplification. For voltage amplification. For voltage amplification. But voltage gain is unity. But voltage gain is unity. But voltage gain is unity. Second observation. CC amplifier can be called as buffer amplifier, but I will explain why it is called buffer amplifier. But write it. CC amplifier can be called as buffer amplifier or voltage follower. This is also called as voltage follower. Maybe the same name we see, or we will see from op amp, voltage follower circuit, right, where V0 is equal to Vi. That is nothing but giving you buffer action. But if you ask me from CC configuration, this is also buffer amplifier and this is also called as voltage follower. Why? Your V0 is equal to Vi. Whatever input voltage you are applying, the same thing is coming at the output. Okay? That's why it is called voltage follower. Therefore, write down CC amplifier. Second observation, CC amplifier is also called as buffer amplifier or voltage follower. Is also called as voltage follower, or another name, emitter follower. This is also called as emitter follower. Emitter follower. CC amplifier is also called as buffer amplifier, voltage follower, emitter follower, because emitter is following your input. That's why it is called emitter follower or emitter follower. There is another name, emitter follower or emitter degenerative circuit or emitter degenerative circuit. Emitter degenerative circuit. Degenerative circuit. Emitter degenerative circuit. What do you mean by degeneration? Actually, regeneration is nothing but positive feedback. Degeneration is nothing but negative feedback. Actually, this is why you are getting gain 1. If you ask me, anyway, I will explain from feedback amplifiers. Actually, it has some feedback. The load itself is the feedback for your CC amplifier, due to which your gain is reduced a lot. Then we are getting maximum feedback. Therefore, maximum gain reduction, which is nothing but unity gain. Okay, whatever it may be. For the circuit, doesn't matter for us what feedback and all. We are just looking for AC parameters and then calculating. Therefore, this is also called as degeneration is nothing but negative feedback. Therefore, we have negative feedback load at emitter. Therefore, emitter degenerative circuit. Okay. Therefore, it can be called as buffer amplifier, voltage follower, degenerative circuit, and emitter follower. These are all the names for alternative names for CC amplifier. Okay. I'll stop now. In the next session, we will see and I'll explain why it is called buffer amplifier, what is the meaning of buffer amplifier, and how to use this buffer action in the case of combination what I told, right? We need to combine like CE and then CC to get impedance matching at the same time voltage gain from CE amplifier. Okay. Thank you.